Good morning, family. It is I, your intrepid teacher, Mr. Romer, here on June 8th, 2020. The time is now 9:34 a.m., and I am broadcasting to you from my home here in Springfield, Massachusetts. I apologize if I am not 100%. The pollen is just crushing me. I just had a sneezing fit, like 10 sneezes right in a row, if not more. If I sneeze during the video, I apologize. I also am nursing a lovely little migraine um, behind your eyes when you get that headache, that burn, pain, stabby feeling behind the eyes. That's what they call a stress migraine. There's a lot going on at Job Corps. Um, some information came out this morning during the Zoom meeting, which I was a part of for a little bit. Then I had to stop because the migraine just really bulldozed its way through my brain. And I just couldn't do it anymore. I couldn't watch the Zoom meeting. Turned off my lights, pulled the shade down. So that's why it's a little dark in here. The little light that's coming through the crack of the window is the only thing I'm dealing with. The computer seems to be seeing me okay. Be that as it may, like I got everything off here. Like this is with the light on. Oh, I don't even have the light on. Thank goodness. I don't want to blind myself, give myself an even worse headache. But there's a lot coming down the pike, and I'm not trying to scare anyone or freak anybody out, but participation is going to be huge over the next couple of weeks. It's going to be part and parcel of what we do as a group. They're pushing hard. I don't like it, but it is what it is. And I am, for the most part, at the time being, a team player. I'm here for you. I'm here for you guys. I'm not here for Job Corps. I'm not here for API or whatever managing group currently has the reins on my bit. But I am here for you guys to answer questions, to help you along in your lives, to make your lives better by educating you and showing you the path and talking to you about the path and really keeping you guys excited about Job Corps. Did you guys hear that? There's a bird sitting on my windowsill. Oh, it's too bright. You guys can't. Oh, he flew away. Like my shades like pulled down to the bottom. Oh, let me see. The bottom open is about this big, and there was a bird sitting right on my windowsill. I love it when Mother Nature does that. I don't know if you guys know, I'm a huge animal fan. Dogs, cats, birds, squirrels, raccoons, possum, birds, some more. Bats. I've had not pet bats, but I did not a bat rescue, but there was a bat that had bonked its head on one of the windows. I don't know how. They don't use eyesight, they use sonar. Maybe a wind gust at night smashed it up against the window. Anyways, I went over and found this all passed out bat on the little ledge next to the window. So I took him in and nursed it back to health over a couple of days. They're super cute. I am also into animal rescue. So a couple of years ago, like 2 years ago, I went and had my boosters for all my vaccinations, so I don't get rabies or I don't get any of the other transmissible diseases. Maybe I'm COVID proof. Who knows? So anyways, so yeah, I nursed a little brown bat. They're about this big. And keep it in a cage, and it totally acts like a little bird, a furry bird with wings, like a mouse with wings. Just very, very docile, not a hostile animal at all. As a matter of fact, I would have loved to have kept it as a pet. Call me Batman. Try not to laugh too hard. Anyways, yeah, so you guys, it's going to be a huge push to have you guys participating a lot. And I know I'm going to lose some of you because of this. And it hurts my feelings because there's nothing, you're not doing anything wrong. It's the expectations that are coming down from the Department of Labor. Well, I don't even know if it's DOL or if it's just API, the managing group, and the staff at Job Corps. And I'm videotaping this and I'm putting it up in a Job Corps classroom, and I don't care because the reality is I'm here for you guys. I'm not here for me. I'm here to ensure that each and every one of you who participates in Job Corps' Department of Labor's automotive group gets a really good education, and I don't do that by insisting you spend 20 hours in a classroom. I do that by being your cheerleader, by being someone who you can talk to, by being someone who puts content out there that you can watch and spend time with and get information from that will apply to you in your life, that you can use it. You know, that's though I can point at several jobs where you can use trigonometry and geometry that you would learn in high school and how you would apply it to work. 90% of the jobs out there do not use geometry. There are 10% jobs in engineering where you need to use geometry. But if you're in engineering, geometry is the least of your worries. You have a lot of other things you have to worry about, of which, like computer sciences, it's just big. The computers do the geometry now. Knowing how to work the computer's the trick. Why do I say that? Because we're trying to teach you guys a whole lot of stuff, and some of it just isn't applicable. The things that are applicable are the things that almost can't be taught. Waking up every morning and putting your knee to the grind, 9:42 in the morning, and I'm making a video to you guys on a Monday morning, not because API pays me a paycheck. That I don't even think about. It's because I like doing my morning meetings with you guys, my morning videos, my lecture of the day. I find it cathartic, which means I feel better after doing it. So if anyone ever says something is cathartic, know that it means I feel better after saying it or doing it. I feel better inside. I feel accomplished. And I know for you guys that doing a quiz or a test of mine or King's on Job Corps probably feels cathartic. You don't want to do it. It hurts doing it. But when you're done, you feel better. And I'm thankful. I'm thankful that you guys who are making the effort, and I respect it, and I am in awe of your ability to live in this day and age and get it done. That's amazing. This weekend I went to 2 separate marches. And I think I talked to you guys about it. A couple. And in and of itself, the whole process of attending a march, protesting, having your daughter make you a sign that you carry, having a brother that marches with you in a march, or if you go with your parents. These are very, very, very tumultuous times. It's tumultuous. It's like being in a washing machine. It's all smashing around and going around. It isn't easy. It is not easy at all. And on top of that, the company I work for wants me to just keep churning out the hits, keep the product flowing, keep things moving forward. Get your kids to spend 20 hours online or they don't get credit for the week. And I have to make this, I got to put ketchup and mayo on it so it tastes good when you eat it. You know, that sandwich that API is making me make. I get it. I get the fact that we want you guys to participate a lot. And I love that. I love it when you guys participate. It makes me happy. But to have it mandated, it goes against certain parts of my insides that scream in protest who I am. So, understanding that, I'll put the content in here and I'll make the videos and I'll make the little quizzes and tests and hope that it is always enough for these meetings. There's something that came up today called Carnegie Hours, which just is a means of dictating how much time a certain quiz or test is supposed to take in the real world. And they'll use that to say, well, if Johnny logs in and does this test, we can give him 1 hour for it. 20 questions plus a video is 1 hour. So if something with 10 questions is only worth in Carnegie Hours half hour, then you as a student have to validate and verify you've done 20 hours of work a week. I'll do my best to help you guys through it. I'll do my best to post as much info as possible, to constantly churn out hits with the quizzes, and that's my job, to make this interesting and as smooth sailing as possible. Without further ado, 9:47. Let's read from the glossary of goodness. What are we talking about today? Allen wrench. Let's start with Allen wrench. A type of hexagonal drive mechanism for fasteners. They make it sound really, really technical, don't they? Imagine a screwdriver. You lop the tip off, now you just have a straight shaft. It's round, like a pen. Hexagon. How many sides does a hexagon have? 6. 6 sides on a hexagon. Heptagon, 7. Octagon, 8. So 1 onagon, 2 duogon, 3 triangle, 4 quadrilateral, or a square, depending on if there's any angles. As long as it's square, it's posi drive. We've heard of posi drive. It's just a square. 5 is a pentagon. We have those for the military. It's in Washington, D.C. That's the Pentagon. Hexagon is 6. Heptagon is 7. Octagon is 8. That's where MMA fighters fight, in the octagon. Nonagon is 9. And then decagon. Decagon is 10, I believe. If memory serves, at Monday morning, no coffee, water, Yeah, back to drinking my gallons of water every day. The aspirin. So you get it. You shave the side so it looks like a stop sign, the shape of the stop sign on the tip of that screwdriver that you chopped the top off of. You now have an Allen key. Whatever the diameter is, you measure it, top to top, edge to edge, and whatever that millimeter size is, the size of your Allen key. You can shave the edges down so it's really small, like for like a 2 millimeter, 3 millimeter Allen key, or it could be real big. You get like a 20 millimeter, like that. That's all an Allen key is. 6-sided screwdriver. They make it sound so difficult when they a type of hexagonal drive mechanism. Drive mechanism is just another fancy way of saying screwdriver. You drive screws in. Drive mechanism. My wrist is the mechanism that drives the thing. So, alloy. Hello there. Hello. English for saying hello. No. Alloy. The mixture of materials to make a substance that has properties different from the original materials. Aluminum alloy has silica added to make it perform better than pure aluminum. Just 1 second. Now this side. It was on that side, now it's this side. Okay, alloy. Aluminum can be found in the earth as well as iron. We talk about steel. Steel is an alloy. It's not naturally occurring. There's no periodic chart that has the element St in it. That's steel. Steel is an amalgam, a mixture of various other things inside. I'll describe it to you. Steel is made up of iron, Fe on the periodic table. It's iron. Iron is naturally occurring. It occurs in the soil. If you take so here's the fun part. You get a really strong magnet. Something you buy at the store, not on the back of a sticker you put on a microwave oven or a fridge door. No, those little silver ones you can get at Harbor Freight. Or if you go to Lowe's, you get industrial magnet, really strong. You go in your backyard. You dig down about 8 inches, maybe a foot, about 5 inches around. You take a shovel and you just go down a couple of times near no roots or anything. You scoop up the dirt. You put it in a cup. You drop your magnet in, cover the top, shake it. Pour everything out, grab your magnet. You will notice there is dirt sticking to your magnet. That is iron. Iron at a very, very small amounts. Now here comes the fun part. You do that. And then you scrape off all of that dirt that's been sticking to your magnet onto a plate. Do it again. Scoop out dirt, put it in a cup, put the magnet in, shake, shake, shake. Pull the magnet out with all the stuff on it. And you make a mound on your plate. You can do this at the beach where there's sand. You can do it in the dirt in the backyard. Not the dry stuff on top. Iron's heavy. It is in nature as it is when it's in an ingot that you've formed. Iron is heavy, so you got to go down into the dirt a little bit to get at it. So you get a big amount, like a gallon jug filled with iron tidbits little grains of iron that you get in the soil. Then you make a fire and you make it really, really, really hot. You had lots of logs, right? Lots of logs, big fire. And the fire burns down and it's got a big mound of embers in the middle. You take a metal pipe that's hollow, like a steel tube. You jam it into the heart of the fire, right? To the end of the tube that you're holding on to, you attach an air hose and you bleed a little bit of air, 1 psi, into the tube. That air goes into the fire and oxidizes. But because you're oxidizing embers that are insulated, it gets really, really hot in there. You take a clay jar that's been fired in a kiln, and we'll talk about that later. Anyways, a clay jar. And you put all of those iron filings into it, and you stick it in the fire. And you cover the jar, the mason jar, the ceramic jar with the top, and then you bury it in ashes. And you turn up the heat a little bit to maybe 2 psi of air going through. So it's blowing. Really heats it up. Always after some time, maybe 45 minutes or so, you take metal tongs and you go and you reach into the fire and you pull out the and you add fire, obviously firewood to it to keep it burning. Doesn't burn out. But you take out this ceramic pot, you've put the dirt that you put off of a magnet that's been in the dirt, and you take the top off and you look inside and you'll see a low liquid. That is liquid iron, what you would normally call in the industry pig iron. Pig iron is a really raw molten iron. So then you take this ceramic, because ceramic doesn't crack under heat, you can put liquids in it, liquid metals, and you let it cool off. You end up with, from a gallon of dirt, you'll end up with like this thick and this wide, a patty, like a hamburger patty of iron, pig iron. And you can take it over, and once you've cooled it, obviously, you don't want to touch it if it's red, because that'll burn you, like a stove. You can take that, you put it between the tongs, and you can hit it with a hammer a few times, knock off any slag or excessive dirt. You can take a metal brush and clean it all off. Now here comes the fun part. So you got this pig iron, this disc of it. If you're best friends with a chemist, you can look on the periodic chart and go, hey, chemist buddy, I have a 3-pound disc of iron. We'll go with 1-pound disc. 1-pound disc of iron. So that 1-pound disc of iron that I've managed to, it's called smelt or melt. But smelting is a little bit different. Smelting is the process by taking and you alloy a metal. So that's what we're going to be doing. I have my disc of iron that I've made from shavings of the iron in the ground. And I will add to it stuff like rhodium or zinc or chromium, which are also elements found in the ground, but they don't get them by melting things that they've pulled off with a magnet. I know rhodium and chromium, they get out of the ground by dissolving metal things in acids. They use acids, really cool, like stomach acids and stuff. And they have a jug full of dirt, and they pour the acids in the dirt and they shake it all up. And then whatever the acid is eaten and liquefied, and it gets to the bottom and then dries up, that's going to be chromium, depending on the acid level, right? So there's different ways of getting at these metals. Nickel's another metal that you can melt at certain temperatures. So varying the degrees of temperature inside the kiln that we were using, the ceramic pot, I made it really hot, which is where everything else goes away and burns away. Iron ore is the thing that stays. Let's say we're going to have a light you're going to have a light fire, not burning incredibly hot. You can extract things like lead out of certain grounds. If you have, if you're near a gravel pit, I think the lead levels are higher near gravel pits, just because lead becomes present in the earth in those locations. But there are certain locations where certain metals will be prevalent, like copper. Copper is prevalent in certain areas of copper mines. You have to dig down deep to get to the copper mines, to get copper. Silver is the same way. There's silver mines. Those are mines found next to indigenous rock. You get veins of it. The earth has already compressed it and made silver. You just got to go dig it out. You don't even have to liquefy it. It's in chunks in between squished rock. Big slates of granite will have copper and silver, whatever, squished inside of it. If you play Minecraft, that's sort of the general idea. You'll dig down through different types of rock, and in different types of rock, you'll find veins, literally like veins in an arm, in the rock. And those are the ore, the veins of silver and the veins of copper that you can dig out. And you can do the same with gold. If you dig, you can dig for gold, looking for gold veins in rock. Modern gold, if you guys watch anything on Netflix, you get the Gold Rush channel, and it shows guys panning for gold, where they're doing it the easy way. They're sluicing. So sluicing is when you take advantage of water, having uncovered the gold in between rocks. But this gold has been now pummeled and smashed by rocks and pebbles, so it's very fine. And so what happens is you run water from the creek where there's gold, where you think gold is, and the water smashes through the rock and creates smaller rocks and pebbles, and those things hammer away at the gold veins, and that in turn gets pushed down the river like silt. And your job is to be at the bottom with a big filter and to get rid of all the junk and try to keep the gold. Now, the one thing that helps these guys is that gold is wicked heavy, slightly heavier than lead, and lead is heavy. How heavy is lead? Easy. Batteries. Those 12-volt car batteries we put in our cars? Those things are filled halfway with lead. Not even completely lead, halfway. And batteries are heavy. Wicked heavy. That's how heavy and dense lead is. Gold is even heavier. So, because of that, these things can be found in the ground, and the magnet was just the thing that allowed us to have access to the iron. The other thing is there are different mechanics for getting to the different types of materials and metals that we use. So here we are. I've got my ingot of my little disc of iron, and I'll go, I need the various things, like I need cobalt, I need rhodium, I need silver, I need chromium, I need nitrates, salts, I need, what else is there? It's a couple of other things, but I don't remember what it is right now. So I take it and I get like a little thimble's worth for each one, and I measure out from the thimble. I get my little itty bitty spoon out, and I measure out little amounts of each of these various other chemicals that I've gotten from my chemistry friend. We had 2 scoops of chromium, 1 scoop of nickel, 1 scoop of nitrates, and I'm going to take another one of that of rhodium, and I'll do half a scoop of that, right? And you add all these percentages of other little things, and then you take this mixture and you put it back into your ceramic bowl, and you put the cap on it so none of it, escapes, and it all stays. Then I put it back in the fire, and I crank up the fire and the embers, and it gets really hot. And halfway through the melting, I'll take it out with my tongs, and I'll shake it to stir it. Maybe even take the top off, and I'll take maybe another ceramic spoon the mixture up, make sure none comes out, put the cap back on, put it back in, right? Turn on the air to press air through the embers in my fire. to make it nice and hot in there. And now the iron ore that we extracted out of the ground has been mixed with all these other metals that we also find in the ground, but we extract in different ways. And we mix it all together. And that mix is called an alloy. So you say, Mr. Omer, why the hell are we doing any of this? I'll go, okay, good question. Iron by itself is a wonderful material, but iron has a couple of things that it doesn't like to do. Iron likes to warm up and cool down slowly. If you warm up and cool down iron quickly, it cracks. It does. It doesn't like to, it likes to cool down slowly when it was hot, and it likes to ramp up and get hot slowly. It doesn't like to get hit with things like hammers. It doesn't like it. It doesn't like to flex or bend. It's very rigid. It's really good at absorbing a lot of energy. You can get iron really, really, really hot, and it doesn't break. So that's good. But other things it doesn't like to do. So you say, well, I'm making an engine. And they're like, okay, well, low RPM, low heat, an engine made out of iron is a good idea. Okay. It's heavy, crazy heavy, but you can make it. Absolutely. As a matter of fact, the first engines were made purely out of iron. Iron blocks, iron heads, iron pistons, iron connecting rods, iron crankshafts. Iron, 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 iron. All iron. They weighed a ton and made 2 horsepower, which back then was a lot. It was a ton of work. 2 horses worth of work. That's pretty good. But as most human beings like to do, they want to make things better. So how do we make the engine better? Make it make more horsepower. Okay. How do we do that? Well, we got to make it more efficient. Okay. We have to make it lighter. Whoa, 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 whoa. What's this lighter business? All right, and we have to make it stronger. Oh, stronger and lighter. Well, how am I supposed to do that? Well, it's a good thing inquisitive minds wanted to know what would happen if you added something to iron and made an alloy of iron. And through time and efforts, and literally men and women in shops adding little amounts of this and that to iron and then cooling it off and then having a machine break it or twist it or heat it up and hit it, they found that various chemicals, various metals added to iron made it behave differently. And when you added a whole bunch of things together to make an amalgam, a mixture of all these other elements, these other metals in with iron, and made a really good mix at the right levels of all the other chemicals, you ended up with a wonderful thing called steel. Steel is fantastic. Steel has properties that you can even add enough nickel and chromium to steel to make it stainless steel, which under normal circumstances does not rust. Its surface shows no nitrates or other alloys that stick up with chemical bonds that allow oxygen to grab on and mix with it, creating oxidized surfaces or rust. Those chemical bonds that iron has sticking out of its molecular structure, stainless steel is a smooth, flat surface. All the chemicals have have interlocked with other chemicals, and all of the chemical molecular connections are accounted for and create a smooth skin of the surface so that other things can't, rust can't grab things that are sticking out and oxidize them. You can't have things come and build on a stainless steel surface, which is why if you make the stainless steel quality enough, it won't rust. You can dip it in ink, nothing will happen to it. It won't color, it won't change. It just stays stainless steel. It's amazing. Problem with stainless steel is it's very brittle. Stainless steel tends to not like to bend. Cracks instantly. It's like glass. However, you can make alloys of stainless steel too. You can add back in other things to make it more flexible. Most specifically is iron. Iron doesn't like to shatter. I was wrong when I first said iron shatters when you hit it with a helmet. It isn't. Iron is ductile. You can hit it with a hammer. You can hammer on iron. You can't hammer steel. I apologize. I was wrong 3 or 4 minutes ago when I was talking about hitting it with a hammer. You can hit iron with a hammer. It bends. Sometimes it bends when you don't want it to bend. So now we have steel. And the great thing about steel is you can cut into it. You can shape it using machines or heat. When it's super hot, you can pour it like a liquid into a form. If you keep adding different things to it, you can make different metals that are no longer steel. They absolutely turn into the alloys section of things. As a matter of fact, you guys have heard of magnesium and titanium. Those are also two chemicals that can be found in microscopic levels in stainless steels. But when you get enough titanium together on its own, which is another thing that you can dig out of the ground, and I honestly don't know how they extract titanium out of the ground. I don't know how it does. I'll research it myself. And you can make parts out of titanium. The one tough thing about titanium is you can't weld on it really well. Welding titanium is like voodoo magic. I don't know how. I don't know how to weld on titanium. I was told at one point, but I've forgotten. Inconel. You guys hear about turbochargers made of Inconel. Inconel is a proprietary alloy made by DuPont. I think DuPont. Where they have mastered the precise amounts of all the different elements that they need of metals mixed with iron, and then they heat it at a specific temperature, stirring it at a specific rate, and they end up with this wonderful steel called Inconel, which is super durable, high temperature stuff. Turbochargers are made. They're blades in a spinning turbocharger on the turbine side, not the cold side. The cold side you can make out of aluminum, which is soft and malleable. You can almost heat it up with your hands. That's lead, but same idea. But the hot side, the turbine side, is the steel that they use. Its particular alloy is called Inconel. You guys can look up what makes up Inconel. So that is why we alloy. We add other materials to steel, or even its more native form, iron, in order to make the iron behave in a way we want. And you can make iron lighter by adding things like nickel and nitrates and salts and things, and it lightens the iron into like a steel, a different type of steel, where it's not as heavy and it's machinable. Iron's machinable, but it cracks. It likes staying its native iron poured self. So that's alloy. You guys can look up videos on YouTube if you want, How do we get iron? What is iron? How do I alloy iron? And it'll have an amazing in-depth analysis where there's production and there's they'll quote sites and sources and books and other things to to prove to you that they've done their homework on it. I'm just coming out of memory, just talking to you one on one about my thoughts on alloyed metals and the basis of that. I'm sure you can find much more in depth, and I hope you do. That's the other thing. I'm not saying don't. As a matter of fact, I'm saying I want you to go and I want you to learn about metals. It's amazing how much there is in this world to learn, and the more you learn, the better you are as a human being. Learning is the thing we do that separates us from the rest of the universe. The human mind learns. And you might say to yourself, well, why do I need to learn about alloys and mixing steels and mixing iron with chemicals? Who cares? And I'll go, okay, initially, sure, I get that. Why bother learning about it? Learning itself does two wonderful things. It expands your mind and it gives you a broader base of information to draw from. And something as innocuous as a conversation with someone, even if it's just ego driven, where someone's talking about steel and you go, oh yeah, I learned about alloys of iron, steel being one of them. They'll look at you like, you know about steel and alloys of iron? Wow, good. Do you want a job in engineering? And you go, sure, I'll get a job in engineering. You get paid the big bucks. But in essence, that's what we do. The more we learn, the better a job we can get, right? Next item. Oh, and by the way, Allen wrenches, that remember how we were talking about first, Allen wrenches are made of steel, a particular tough, durable steel called tool steel. Tool steel is iron made into a steel by adding certain ingredients and then adding one last ingredient called tungsten, which can be found in the ground. I think it's native. I have to remember on the periodic chart if there's tungsten. I think that is. But you add tungsten to steel, and you have tungsten steel, and that's tool steel. Super strong, super brittle, but really effective at keeping a sharp edge. Iron doesn't keep a sharp edge, softens up super easy. Try to sharpen iron, and it stays an edge till you cut a couple of apples with it, and it goes dull. Still strong. It's you could smash the apple, but a sharp edge. Edging something is super. That's a big metallurgy thing. There are a lot of scientists mixing iron with all different chemicals to find the perfect edge making material. Something that you sharpen once and it stays sharp for a very long time. So much so that they looked into polymers, plastics, ceramics. You guys remember about 5-10 years ago, there was this huge craze. Ceramic knives never needs to be sharpened. Bullshit. Everything needs to be sharpened. It's just how much longer you have to wait. And ceramics does hold its edge really, really well. But believe me, because there are ceramic blade sharpeners out there that resharpen old ceramic blades. And so you have to say to yourself, well, if ceramic never needs to be sharpened, well, why are they selling ceramic sharpeners and why are they selling well? And the reality is because they're not really never need sharpening. They do, just not quite as often. That being said, and ceramics is a neat thing. I think ceramics is the mixture of clay and grains of sand that crystallize into glass. and it's a mix of those two and a couple of other things. And you dry it out. You dry the ceramic out so much that zero moisture is inside of it, but it retains its shape and structure, which is why you can use ceramics to melt steel in. Ceramics that has no water in it, so it won't crack, it won't break, it just sits there. It's really cool. Ceramics are really cool, fun stuff. And you guys should do Google search and YouTube videos of ceramics and how they fire ceramics in a kiln, how they heat it up and get all the air, all the moisture out, and why it's so strong. Yeah, they make ceramic knives. No metal in it at all. There's no iron, there's no steel, no metal. Ceramic. It's clay and glass. It's really cool. Ooh. 10:20. 45-minute video so far. Not bad. So that's an alloy. Oh, and it talks about aluminum alloy has silica. Silica is grains of sand, also known as glass, added to make it perform better than pure aluminum. This is true. Silica's a constituent of glass. You can't take a cup full of sand and melt it down and make glass. That's not how it works. Glass is its own, and sand is one of it, but particular sand from particular types of beaches that is particular makeup of sand. When you look at it under a microscope, sand is a lot of different things. Sand is the ground up shells of mollusks, which are clams and oysters and stuff like that. Sand is also a mixture of rocks that have ground themselves into dust, and that dust is part of the sand. Sand is the bones of fishes and all the things that swim in the sea. Sand is also a mixture of ground up because the waves constantly lapping up on the shore makes those little grains rub up against each other. So they're always becoming finer and finer a grain. And another thing that sand is silicates, which are the bodies of diatom. So these are things that you guys need to look at under a microscope. It's really, really, really cool. There are creatures in the sea that are microscopic. You don't even see them. They're just so small. And these creatures create shells for themselves. And these shells, then when they die, they wash up on the shore and they beat up against other shells. And they make, basically, this is all sand. And so when you take the sand, you melt all those little things together. And one of them is silica. And with the right mixes, and you add some things, and you get glass. Yeah, it's pretty wild. And glass is its own special world. Matter of fact, I'll do a video on glass, how glass is made. That's today's video. That's the magic word of the day, is glass. Glass is the magic word of the day. We're going to do it. So, anyways. Yeah, because tomorrow, all-wheel drive. And then alternating current. All right, so Tuesday, all-wheel drive. Wednesday, alternating current. Thursday, alternative fuel. Friday, aluminum rod. Aluminum. So aluminum is something you find in the ground, just like steel, but it's non-magnetic. Magnets really don't pull on aluminum that well. Iron reacts strongly in a magnetic current. Aluminum, nah, a little bit, little bit, but nothing where you can use a magnet to get at aluminum. Aluminum reacts to other things. Heat, it melts a lot lower temperature than steel. A lot lower, thousands of degrees for steel. Aluminum goes at like 1100 degrees. something like that, 1150, 1200. Steel's up into like the 4,000 to 5,000 range. Hot, 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 hot. Takes a lot of temperature to melt steel. Melt iron is like iron 4,500 range, something like that. No, not that high. I'll research it. You research it. I'm here to give you these ideas. You go find the particulars, the nuance. But definitely that's the layout. Aluminum rod for Friday, ambient air temperature sensor, American Petroleum Institute, American wire gauge. We'll cover those maybe on Friday. But definitely Tuesday is going to be all-wheel drive. Wednesday, alternating current. Thursday, alternative fuel. Friday, maybe we'll talk aluminum rods. We'll make it a rods day. We'll talk about rods. Eagle, Hart, Carrillo, all the different rod manufacturers and why they're, an Eagle rod's fantastic and a stock one sucks. We'll tell you why rods are important. So we'll talk about aluminum rods on Friday. Matter of fact, let me write that down because I have to submit my lesson plan. So Monday was Allen wrench. Word of the day, glass. And we all talked about alloys. Tuesday, we'll talk about all-wheel drive. Wednesday, we will talk about alternating current. AC, not air conditioning, AC, alternating current. And Thursday, alternative fuel. Alt fuel. And Friday, aluminum rods with an emphasis on rods themselves. That is our scholastic week. We're at 10:26, excuse me. Time to stop the video and time to make I'll make a little segue video. I'll pull something up on glass. And that'll be glass will be my fun quiz of the week. Ta-da! All right, everybody, high five.